Hi everybody, just wanted to make this video setting this up. Alright, set this up. I want to just kind of finish this off. I guess it's a problem that I didn't finish solving, so it's just bugging me. Here's rolling without slipping. I'm going to solve it using energy. So again, we got a ball here, we've got a mass M, we've got a potential energy UGI, and then that all gets converted into kinetic and kinetic energy, rotational kinetic energy, and translational kinetic energy. And you can see that right here. Moment of inertia for a sphere is 2/5 mr squared. You can look that up. And then omega equals v over r. So this is kind of the equations we're going to use. As I did in class, the energies are conserved. Potential energy gets converted into rotational and translational kinetic energy. And so I'm going to kind of keep going here. So I'm going to replace omega with v over r, so omega is going to get replaced with v over r, and then I is going to get replaced with 2/5 mr squared. So it's going to be mgh equals 1/2, and then I is 2/5 mr squared. This is kind of nice, these 2's cancel. And then I got, instead of omega squared, it's going to be v squared over r squared, because that square distributes, plus 1/2 mv squared. And then lastly, those masses cancel out conveniently. So I got GH equals, these R's cancel out as well. So I got, what's that going to be? V squared over 5 plus V squared over 2. Common denominator here is 10, so I could replace these with 10. This will be 5, this will be 2 and 10. So 5 plus 2 is 7. So this is going to give me 5 plus 2 is 7. So I got, whoa! Wow, that's a lot of color. So GH equals 7 out of 10 V squared. So then I can just solve for, so I got 10 over 7 GH square root, and that's my speed. And notice, right, it does not depend on the radius like you guys saw in your Pivot Interactive Lab, and it doesn't depend on the mass either, this final speed thing. Alright, so now we're going to try again, except this time using F net equals ma and torque net equals I alpha. This ends up being a little bit more, as you can see, it's already more involved. I drew out the forces in class. So here's my free body diagram of the forces, and I'm going to use that free body diagram. Remember, this is mg sine theta, this is mg cosine theta. And so F net equals ma, I'm just going to do it in the horizontal direction. So in the horizontal direction, this is going to be my positive direction. I'm tilting my axis like this. And it's going to be x equals mg sine theta minus the force of friction equals the mass times the acceleration. And I think that's that. I'll leave that at that for right now. So that's my first relationship. Now let's use torque net equals I alpha. So using torque net equals I alpha, I get that the only thing creating a torque is this frictional force. This frictional force here is the only thing creating a torque, because the sphere is rotating about its center of mass, and so the torque is the only force exerting a torque that's anywhat perpendicular and away from the axis of rotation. So that's RF sine theta. Theta is going to be 90 degrees, so it's just going to be 1. And I'm going to isolate R. So we're going to get the force of static friction is equal to, oh, this is nice too. So yeah, I'm going to isolate the static friction force. So this is going to be 2/5 mr squared times a over r squared, because I divided both sides by this r. So the r squared ends up canceling out, and I get the force of static friction is equal to 2/5 ma. So then that's my second relationship, and I'm going to plug in that 2/5 MA into my static friction force here. So that's going to be 2/5 MA, so this is going to be mg sine theta minus 2/5 MA equals MA. I'm isolating for the acceleration because I'm going to plug it into a kinematic equation. First off, all these masses cancel out, which is good. That's what I got in my original solution. And now I got g sine theta, and then adding that 2/5 a to the other side. This is going to be 5/5a plus 2/5a. So that's going to be 7/5. So 7/5a, I think. Yeah. This is g sine theta. Alright, and then I'm going to isolate a, so it's going to be 5/7g sine theta equals my acceleration. And I'm going to now plug this into a kinematic equation. Hold on to this. And the kinematic equation I think I'm going to use is v squared equals v naught squared plus 2a delta x. Take the square root of everything. So the initial velocity, this starts at rest, right? Even in the original problem, it only had potential energy, so the initial velocity is 0. So this is going to be 0 squared plus 2 times my acceleration, which is 5/7 g sine theta. But now I need to figure out what delta x is. So in order to get delta x, well, the distance that delta x travels, that's going to be from here to here. That's delta x, right? So I can use this is the height, h. So I can use a little bit of trigonometry. Here's my angle theta. So that would give me sine of theta is h/delta x. So I'll do that kind of off to the side here really quickly. So sine of theta equals h/delta x. Isolating delta x gives me h/sine theta. I'm going to take that and plug it in there. So that's going to be h/sine theta here. And sure enough, sine thetas cancel out. Oops, not the key. Sine theta cancels the sine theta. And I get v equals 2 times 5 is 10. So the square root of 10/7 gh. That looks close. Is that what I got before? 10/7 gh, square root 10/7 gh. Checks out. So just kind of showing you both ways work. Alright, hope that helped. Bye.